write the GR conformation of this. So let's draw. This is up, above. This is also above. So we get this. So another conformation will be both the group in the axial form, but I will not draw that axial form because both will be in the axial form. So then the 1-3 diaxial strain will be of severe because here is a NME2 group and here is again a bulky group. Both are in the axial position, then that will be very less, almost no percentage of that conformation. So reaction will solely go through this conformation. So I will talk about this conformation. So here what happens that this conformation, here you can see, and we know that for the fragmentation reaction, the electron donating group and electron withdrawing group has to be a good orientation. So that dictates, and the position and the stereochemistry and of those group dictates the possible positions of the bond cleavage. So let's try to see that. So if this lone pair pushes back, then this group, which is exact parallel to this bond, okay, so that's the reason this feasibility of this simultaneously bond formation and bond broken is made feasible. So what we get, we all know that the system, the reactant, there was ethanol and water, so both can cleave this, and this will be ejected as NH2. So this will be carbonyl. So I am not showing that reaction, so I am just gonna write the product, which is, that will be the product. If you want to see the orbital picture for the responsible for that, so I can say that here is a sigma orbital of this bond parallel to this, and here, so let's show the phases. So here is a sigma star of that. So both comes into good handy in the orbital contributions respectively. That is the sigma star and that is the sigma. So they are the perfect conformation for the reaction. So let's get back to another conformer, which is another diastereomer. Same we can draw chair form. This is up and this is down. Same way we can write another conformation, which will be through in flipping. So where it will be in the axial position. This is the NME2 group, and this will be here. So as we can see that this ME group and this has also C3 hydrogens are there, so that will be severe repulsion with these hydrogens, both the axial hydrogens. That conformation will be very low in concentration, but still, as this OTS is not in the axial position, so concentration will be some amount much more than this diaxial conformation concentration. So that will be minimum, but this will be the maximum concentration. So some part of reaction will be carried out through this. So what happens now, corresponding to this, there are two axial hydrogens in two positions. So in the reaction medium, another reagent was triethylamine, so which is a very good reagent for elimination reaction. So what happens, this takes one of the hydrogens, goes here, this here. These gives two types of positional, two types of product which are not isomer, I can say positional isomer, something like that you can say. So the product will be in is here. So after that one double bond will be here, another product will be. So two types of product. And from here what happens that this lone pair donation from the carbon is obvious that will happen, because that doesn't depend on the axial or equatorial position. So it reverse back. Now this bond and this bond are parallel to each other. They are in a good orientation for bond fragmentation. So what happens, this goes here, this comes here. So one of the minor product will be just like this, same product after hydrolysis, of course. So we are given a Decarin system. So the most important thing in this case is to draw the proper chair conformation in this type of system. So we are given the junction is trans, so we draw the trans Decarin. Trans Decarin will be two chair cyclohexane will be in a trans junction. So what will it look like? So trans junction means there will be two groups which are trans to each other. So this is up, this is down. So there will be another trans. Okay, so this is hydrogen, this is O minus, and this OTS is up, so this will be in here. So what happens, this O minus pushes back, this bond and these bonds are in parallel position, so the cleavage will be from this end, this goes here, this backs here. So what we get? We get the important thing is that this is the trans double bond we have produced. This is a 10-member ring has been formed. Let's take a look of the other diastereomer. So this is a cis Decarin because the hydrogen and O minus are in the same plane. So we will draw cis Decarin. So for the drawing we will draw at first a cyclohexane. So now H and O are in the both in the down, so we will draw just these things. So this will be up, so this will be in this position, and this will be also up, this will be in this position. The rest of thing is we have to draw the parallel of this. This goes here and joins it. So this will be the cis Decarin. So this is the hydrogen which is down, this will be the O minus which is down. So this OTS that will be also up. So what is the up? If you can see in the another angle, which is from this angle, if you can visualize this cyclohexane chair, so this will be the up state, this will be the above the plane, so OTS will be here. So now we can visualize the stereochemistry. So if this O minus gets back, this bond and this bond are in parallel, this goes here, this goes here. So the product we will get will be like this. Will double bond O, that will be here, and will be the concerned double bond, it will be here, it will come here, it will join. So again the double bond is formed here, it is trans. So now we have got another diastereomer. So now this is also a cis Decarin, but both the groups are above the plane. So now we will draw the reverse, another chair which is a reverse of the previous, which is a flipped form. For the simplicity of the drawing, nothing else. Okay, so this hydrogen is up, so the cyclohexane chair will be down. This is up, cyclohexane chair will be down. Now the rest of the thing is, this will be parallel to this one will be parallel to this. Rest of the thing will be joined. So hydrogen is up, O minus is also up, the OTS is also above. So from this angle here, OTS will be in the axial position for the above the plane conformation. Sorry, the OTS will be below the plane, that is this in this previous conformation. So the OTS will be here. So again O minus pushes back. So this bone and this bone are again parallel conformation, parallel orientation, let us say. So this bone goes here, this clips. So what we get? We get drawing is not that accurate, but what you can visualize is that this is a cis double bond. So this of three of the either of this conformation may appear in GATE exam or CSIR NET exam, and also in a JEE main and advanced exam. There is nothing a big deal in this type of reactions, just a few orientations of the bonds which dictates the reaction, the course of the reaction, the stereochemistry of the reaction, the position of the double bonds, and the isomerism of the double bonds, whether it will be trans or cis. So you have to just learn how to write and how to draw the chain conformation, the cis and trans decoupling. So that's you all have to know, nothing much. So here we are given this compound which is treated with the base. You know that in place of this the alcohol will be deprotonated, there will be O minus. And here we the same thing again, which is you have to determine the actual position, the chair conformation of this group and this group. That will be all. So we are not worried about these groups. So we will just write in the chair conformation the 6-member group attached to it is 5-member group. So let's draw. So at first we will see that this junction is trans because this is up, this is down. So we will draw trans, not decoupling, because this is 6-member, this is 5-member. So let's see. At first we will draw a chair conformation of cyclohexane. Here is the Ame, here is the deprotonated alcohol, actually hydroxy group. So now how to write the 5-member ring? Just like 6-member ring, just one bond less. So just draw here, and this connects these two ends. I couldn't draw perfectly, but this is the case. Just one bond less, one atom less. So here this will be in the equatorial position, this is the up position, so TS will be here. So again we can see if this goes back, this bond and this bond will be in the perfect orientation for the bond cleavage. So the rest is in the as usual. There will be some groups just here, so we are not worried about. So just read the explanation happens, nothing more. This will be the product. So we are given this product, this thing which is treated with HCl. So at first what happened, that H plus will be protonate this carbon, and after protonation this carbon will act as a better electron sink that will draw electron density towards itself. So we can see that here is a bridgehead. We know for our previous experience that bridgehead can move or can donate its sigma bond. Okay, so what happens here, that there is a two bridgeheads. What happens, one of these bridgeheads, because there are some possibilities, because at first what happens, that this double bond can be moved in this way. So what we get, these two chemistries are doesn't affect in this reaction, so I am not drawing those things. So there will be a positive charge. Sorry, I have drawn wrong thing. We will get these things, so there will be a positively charge. Now to stabilize this carbon cation is very much unstable, because this will be junction of a two ring, so that we have to neutralize. So what happens to neutralize that, the bond migrates. So which bond will migrate? So from this bridge center, this bond migrates. Any other bond can migrate, you can draw with yourself, but if this one migrates, a more stable, okay, more stable carbocation will be generated. So let's draw that. This one comes here. So this will be the tertiary carbocation, which will be very stable. There which is 1, 2, 3, 4 member group. So I can redraw it here like this. So we know that in the reaction medium there will be enough Cl minus which will attack here, because we know that nucleophilicity of Cl minus is moderately good. Okay. So if there is any carbocation so present in the reaction medium, so it can react there. So after that, this bond will always have a greater tendency to automerize, because C double bond O energy is greater. This comes here, this goes here, this comes here. So after that carbon will be protonate automatically. So we will get a second similar type of problem has been set. Here also at first protonation takes place. This acts as electron sink. What we can see that here is no electron donating group, but we also have to remind that if there is a strained ring, that can also act as a electron donating group, because that will be a sigma donor. Okay, so that will be donate the sigma donation. How? That will migrate as its sigma bond. So if this sigma bond migrates, there will be a formation of a 3-degree carbocation, which will be very stable. So this bond will have a tendency to migrate, and also this will be again in a conjugation. So this bond comes here, this bond goes here, this comes here. And again, like previous, this is have to get automerized. So it comes back, this comes here, this comes here, the carbon ion. The carbon ion only simultaneously takes a proton. And again there is a medium, there is a large amount of Cl minus, as it is HCl, so that will be again attack this carbocation, because the reactivity of this again will be very high. SN one reaction. So we got this product. This has frequently come in CSIR NET gate exam. This type of problem where there is electron sink, it will be designated as a strained 3-member ring, which can act as a sigma donor, and electron sink will be a ketone which will be connected to the strained ring within a by extended conjugation of double bond.